Hello everyone, welcome back to Chemistry 2 class. We are still on chapter 2, which is on chemical kinetics. So in the first part, I have discussed with you about the calculations. Do you think that you already understand about the calculation and have you mastered on how to make use of the formula and also solve problems? Okay, actually, if you did, okay, you can just skip straight away to the exercise part. If not, let us do some kind of recap on the calculation part from 2.1 to 2.3. Alright, so this is where we stopped in our previous class on the integrated rate law. Okay, so how do we get to the integrated rate law? That is why it's important for you to look at the rate of reaction. Let me just mention, for your level, we are just going to deal with first order reaction, second order, and also zero order reaction. Alright? Okay, so now, actually we start with the rate of reactions. So rate of reactions is equals to the change in concentration over change in time. Okay, and then if we were to write the rate of disappearance of A, we can write it as this way. Okay, it's all the same for all orders. Okay, and then we have what we call as rate law, in which it will equate the equation between rate and also concentration. Okay, and then for first order, the power is equal to 1. For second order, the order is equal to 2. For zero order, the order is equal to 0. So the rate will just be equals to K. Okay? Alright, so now rate of reaction and rate law, if we equate them together, we will get to the differential rate law. Actually, differential rate law is not much of importance. Okay? What is important is we integrate that differential rate law. Okay, so we will get to the integrated rate law. Alright, so this is how you do the integration if you want to know how. Okay, but what it is important is this for you to learn about the integrated rate law. So you must know this equation very well. Okay, that you have the linear equation. Okay, it's just easy to know the linear equation straight away. Okay, so for this equation, it correlates, for the integrated rate law, it correlates the concentration and also time. Why is it important? Because you can start to make prediction. Okay, if I leave this reaction for maybe 2 hours, what will happen to the concentration? So that is why it is important for us to know about the integrated rate law. Alright, so for this integrated rate law, you will get the straight line equation, okay, which is y equal to mx plus c. So this is the same for all first order, second order, also the zero order. Okay, so here, for example, the ln A for first order reaction, ln A is going to be equal to the y, okay, negative k is going to be the gradient, x is going to be time, y-intercept is going to be the ln concentration of initial. Okay, so this is going to be the linear plot. Okay, this is also going to be the linear plot for second order, and this is going to be the linear plot for the zero order reactions. Okay, so sometimes you will be asked to make a plot, okay, to determine the order of fractions, okay, or sometimes you need to use the graphical method, okay, for you to calculate some kind of maybe the gradient, okay, which is the k. So sometimes we can say that you need to use graphical method, so you need to know how to plot the graph. Okay, alright, so now from the integrated rate law, okay, actually you can derive the half-life. Okay, half-life is basically the time that is needed for the concentration of, for example, A, okay, to be reduced by half. Okay, so that is why this is called half-life. So now here, when I substitute the half-life definition into the equation of the integrated rate law, I will get the half-life equations. Okay, so these are the 4 important parts that you need to know out of this whole table. Okay, how you write the rate of fractions, how you write the rate law, the integrated rate law, and also the half-life equation. So most of the time, question will just like play around these 4 parts. Okay, which of the following is the best kinetic plot to confirm second order reaction? So if you want to plot, so what is going to be the plot of for the NO2 against the time? Okay, this is question asking about the integrated rate law. Okay, so for this integrated rate law, because it's second order, okay, the straight line equation is y equals mx plus c. Okay, so the y is 1 over concentration of NO2, okay, equal to m is kT plus 1 over concentration initial. Okay, so this is going to be your y, this is going to be your x. Alright, so in this case, the only right answer is going to be C. Right? Look at this one. Hydrogen peroxide will react following first order reaction at room temperature with a half-life of 866 seconds. So this is your half-life. Okay, so you can write this is your T half. Okay, so now the question said determine how long it is required for 85% of the reactant to decompose. Okay, 85% of the reactant to decompose. Decompose is 85%. So the left amount is going to be 15%. Therefore, we know that the concentration of A, which is the concentration of H2O2 at time T, is going to be equal to 0.15 times initial concentration, meaning to say 15% from the initial concentration, whatever it is. Okay, so now we can find the K value through the half-life equation, because we know that half-life equal to ln 2 over K. So we can find the K, which is 8 exponent minus 4 per second. Okay, make sure you get the unit right. Okay, so next is that we are going to look into the how do you calculate this. Okay, so I'm going to use this equation. All right, so I just substitute the AT with 0.15 times A naught. Okay, so and then we just solve it. We get the time to be 2370 seconds. Okay, all right. Here, okay, the rate constant for the decomposition of herbicide H is 2.25 year minus 1. If herbicide H with an initial amount, okay, so what is this? Initial amount. Okay, so we know that this is concentration of H naught, initial. Okay, this is the amount that is being dumped into the lake. So now, calculate the concentration of the herbicide after 3 years. Okay, so first, we need to know which equation we want to use. Okay, this is for sure is an integrated rate law, because it is asking about the concentration at certain time. So you know this is integrated rate law. But the question is, which order of fraction that we are going to use? Is it zero order? Is it first order? Or is it second order? Okay, so how do we know that this is a first order reaction? Okay, so this is through the K unit. Okay, so if the unit is time minus 1, so we know that this is first order. Okay, so you can scroll back to the table. Okay, I have put there the unit. Okay, so now we already know the K. Okay, we already know the K, we know the T, and also we know the initial concentration. So we just go straight away calculate it. Alright, so now this one is going to cancel. Okay, and you put in the calculators and you solve for the concentration of H after 3 years. okay, you will get the answer to be 3.044 exponent minus 8. Okay, so that's it. If you have any problems or you have any questions you would like to ask, feel free to ask me. Okay, so now we are done for our recap on the calculation parts and also look into the calculations. So you need to do a lot more of exercises, okay, and then you are good to go. It's a bit, okay. This is the recap of overall part that we have learned. Okay, you have zero order, first order, and second order. About the nth order, you do not have to really worry. Maybe you just need to know how to derive the units of the rate constant. Maybe that. Okay.